A single phase transformer like this is supplied from a constant voltage, constant frequency source from the primary side and connected to a load on the secondary side. In most cases, the load would like to see a constant voltage appearing across it independent of the load current I 2. However, in a practical transformer, it is usually not the case. Albeit small, there will be some variation in the load voltage depending on the load current. This can be predicted from the approximate equivalent circuit, which we draw refer to the load side now. Just say these are Req, Xeq. The magnetizing branch, the applied voltage referred to the load side is V 1 dash. This is the load impedance ZL, the load voltage V 2, this is the load current I 2. Obviously, V 2 dash is not same as V 1 dash for all values of load current. This is due to the drop in the series impedances. Also, it will also depend not only on the magnitude of I 2, it will also depend on the phase angle of I 2 with respect to V 2. Now, one important performance parameter of a single phase transformer is its voltage regulation, which is a measure of the variation in the load voltage with variation of the load, that is percentage regulation, full load percentage regulation of a single phase transformer is defined as V 2 at full load minus V 2 at no load divided by V 2 at full load, or that is V 2 at no load minus V 2 at full load divided by V 2 at full load. That is how much the output voltage varies as a percentage of its rated voltage from no load to full load. This is called the percentage regulation of a single phase transformer, and it is a very important performance parameter for a single phase transformer, because this indicates how constant the voltage will be as the load varies. Now, from the approximate equivalent circuit, it is simple to calculate this percentage regulation, since we see that the voltage drop is entirely due to the series impedance. In order to calculate percentage variation, we can neglect the shunt branch. Therefore, the equivalent circuit for calculating percentage impedance will be Req j Xeq. The applied voltage is V1 dash and the load voltage is V2, the current is I2. Let us draw the phasor diagram. Say this is the load voltage V2, load current I2 at a power factor angle of phi. We can draw the phasor of V1 by noting that V1 equal to V2 plus I2 Req plus j Xeq. This is I2 Req. This is j I2 Xeq. This is V1 dash. Therefore, one can write V1 dash cos delta is equal to V2 plus I2 Req cos phi plus I2 Xeq sin phi, and V1 dash sin delta equal to from the previous examples. We have seen that the values of Req and Xeq are very small. They are in the percentage or per unit terms, they are around 7%, 2%. So, the quantity V1 dash sin delta or the angle delta is usually very close to 0 for a normal transformer, even at full load. Therefore, V1 dash cos phi cos delta is approximately equal to 1. Hence, V1 dash is approximately equal to V2 plus I2 Req cos phi plus I2 Xeq sin phi. However, so at a load current I2, the load voltage V2 is given by V2 is approximately equal to V1 dash minus I2 Req cos phi minus I2 Xeq sin phi. Obviously, at no load. So, this is V2 at load and V2 no load is obtained by putting I2 equal to 0 here. So, this is V1 dash. Hence, percentage regulation is defined as V 2 no load minus V 2 at load divided by V 2 at load, but V 2 no load equal to V 1 dash, therefore, percentage regulation equal to V 1 dash minus V 1 dash minus I 2 dash R E Q cos phi minus I 2 dash x E Q sin phi divided by V 2 at load, or percentage regulation into 100 because of the percentage. So, the per unit regulation in per unit expressed as a per unit of rated voltage is equal to I 2 R E Q by V 2 at full load into cos phi plus I 2 x E Q by V 2 at full load to sin phi. This can be written as this is equal to I 2 divided by I 2 at full load into I 2 full load R E Q by V 2 full load cos phi plus I 2 by I 2 full load into I 2 full load x E Q divided by V 2 full load sin phi. However, this quantity has earlier been defined as the per unit load x. This quantity has been defined as R E Q per unit there, and this quantity has been defined as x E Q per unit. Hence, the per unit regulation can be written as at any fractional loading x is equal to x into R E Q per unit into cos phi plus x E Q per unit sin phi. Where the angle phase angle phi is assumed to be positive if the load is lagging and is assumed to be negative if it is leading. From this expression, so this is the general expression of per unit regulation. For lagging load, phi is assumed to be positive, for leading load, phi is assumed to be negative. So, it is imperative that percentage regulation can be 0 at leading load. So, at what value of cos phi the percentage regulation is 0. So, for 0 percentage regulation, 0 regulation, we should have phi equal to x e q sin phi or tan phi equal to or the angle phase angle at which percentage regulation will be 0 equal to tan phi tan inverse R e q per unit by x e q per unit. This is leading, this is the leading angle. So, at this value of leading phase angle, the percentage regulation will be 0. That is, the at this leading phase angle, the percentage regulation at any load, will be 0. So, the terminal voltage under load condition will be same as the no load voltage, and if the phase angle leading phase angle is larger than this, then the percentage regulation will be negative, because this term will be larger than this, which means physically this will mean under load condition the terminal voltage will be larger than the no load voltage. So, this is a condition against which we must guard, because the equipment connected to the transformer will in that case see a voltage which is even larger than the no load voltage and may damage the equipment. Similarly, it will be interesting to find out at what load power factor angle the percentage regulation is maximum. This is obtained by differentiating the expression. So, for maximum percentage regulation, we will have d d phi of cos phi plus x e q per unit d d phi of sin phi should be equal to 0, or x e q cos phi should be equal to R e q sin phi, or tan phi again equal to x e q by R e q, or phi equal to tan inverse x e q by Req, but this is lagging. So, if you draw the percentage regulation versus phi, this is the lagging direction, this is the leading direction, please note that at unity power factor percentage regulation is not 0, it is some positive, it is 0 at some leading power factor. Let us say at this power factor, this value of phi is equal to, we have found this value of phi to be tan inverse Req by Xeq. Similarly, there is a power factor phi, the leading zone where the regulation is maximum, which is this value. So, the power factor, the percentage regulation if you draw, appears somewhat like this. At this point it is maximum, at this point it is 0. This value of phi equal to tan inverse Xeq by Req, and this value of phi equal to minus tan inverse Req by Xeq. This is how the percentage regulation of a transformer, which is a measure of how much the output voltage varies depending on the load current, can be plotted against load power factor angle. And of course, it is proportional at any given power factor angle, it is proportional to the percentage loading. Now, let us look at a problem of how to find out the percentage regulation and the output voltage of a transformer. Let us consider a 11 kV by 440 volt single phase transformer, 50 hertz, 11 kV by 440 volt single phase transformer. This transformer, from the short circuit test data and 75 kVA, short circuit test data gave the applied voltage VSC equal to 310 volts, ISC equal to 11 ampere, and WSC equal to 1.6 kilowatt. In order to find out percentage regulation, we need the series equivalent resistance and the reactance. These are obtained as first we find out ZSC. ZSC equal to VSC by this is rated current, that is not 11 ampere, this is 11 kV, (75 kVA) by 11 kV. VSC by ISC equal to 310 volts divided by ISC, which is 45.47 ohm. Req therefore equal to WSC divided by ISC square, which is 1.6 into 10 to the power 3 into 11 square divided by 75 square. This comes to 34.42 ohm. Xeq equal to ZSC square minus Req square and comes to 29.71 ohm. Now, we have to convert them to per unit values. So, referred to the short circuit test is done on the HV side. So, V base equal to 11 kV and kVA base of course is equal to 75 kVA. Therefore, Req per unit equal to 34.42 into kVA base divided by voltage base square. This gives 0.0213. Xeq per unit equal to 29.71 into kVA base, it is 75 kVA divided by 11 kV square, 0.0184, and cos phi, let us say this transformer is loaded at load with a power factor angle of 0.8 lagging, and at half load, that is x equal to 0.5. So, regulation per unit Pu should be equal to x into Req cos phi plus Xeq per unit Eq sin phi equal to 0.5 into 0.0184 into 0.8 plus 0.0213 into 0.8 plus 0.0184 into 0.6. This comes to 0.01404. So, percentage regulation equal to 1.404%, which means the percentage regulation is by definition V2 at no load minus V2 at load divided by V2 at full load. So, V2 at load will be V2 at no load minus V2 at full load into percentage regulation. Now, V2 at no load is given as 440 volts. V2 at full load at the same power factor can be obtained from the same formula. Into 0.01404 However, it is not necessary because this is multiplied by a very small factor. So, changing V2 at full load actually will be given by V2 at no load minus V2 drop, but the magnitude of V2 drop is much smaller compared to V2 at no load, and when it is multiplied by this regulation, this becomes even smaller. Therefore, in all practical purpose, this can be assumed to be equal to this. So, V2 at load equal to 440 into 1 minus 0.01404. So, this is how from the percentage regulation, the given short circuit test data, the percentage regulation of a single phase transformer can be found, and with that we can also find what will be the output voltage at any given load. So far we have seen that most of the parameters, equivalent circuit parameters and performance parameters of a single phase transformer can be found from short circuit and no load test data. And we have also seen how these tests are to be done. It is important to choose the right equipment for performing these tests. So, let us see an example how we will choose the meters and other equipment for performing these tests. Let us say we have a 200 volt by 400 volt single phase transformer and rated at 4 kVA. I want to perform no load and short circuit test on this transformer. So, what should be the rating of different equipments that I should choose? For this transformer, the rated voltages are for the LV side 200 volts, for the HV side 400 volts. Rated currents for the LV side, it is 4 kVA by rated voltage equal to 20 amperes. For the HV side, rated voltage is 4 kVA divided by rated voltage equal to 10 ampere. So, for the LV side, ratings are 200 volt 20 amperes. For the HV side, rated voltages are 400 volts 10 amperes. Let us look at the first the short circuit test. This is done on the HV side. So, it will be done on the 400 volt side. With the 200 volt side shorted. The measurements required are, you will have to measure the voltage, you will have to measure the power, and you will have to measure the current. Normally, when the transformer is shorted, it requires very little current to very little voltage to circulate the full load current. Therefore, this is supplied from a single phase variac. So, the equipment required are this is the rated 220 volt or 230 volt single phase supply. Equipment required are first is single phase variac. It should, its input voltage is 230 volts. The output, it should be able to carry at least the rated full load current of the single phase transformer. So, its output current should be at least 10 ampere. Then we need a ammeter, which is a should be able to measure AC. So, this is moving iron type ammeter. This should be able to measure 10 amperes of current. Next, I need a wattmeter. This current coil should be able to carry at least 10 amperes. What about the voltage coil? Potential coil. Now, for a single phase transformer, if we look at the equivalent circuit of a single phase transformer, when we short the secondary side, the required voltage to circulate full load current is the series impedance multiplied by the full load current, which under usually is in the range of 5 to 10% of the rated voltage. Therefore, for the high voltage side, the rated voltage is 400 volts, and at best 10% of it which will be required. So, the applied required voltage in no case will possibly exceed 50 ampere. So, let us choose a wattmeter whose potential coil can read at say 100 volts. It may be even lower, can be even 50 volts possibly, but it is difficult to get a wattmeter of that rating. So, let us choose 100 volt. A 75 volt is a normal rating that is usually available. So, it may be even 75 volts. Then we need a voltmeter, moving iron voltmeter. Since the potential coil of the wattmeter and the voltmeter are connected to the same points, the drop across the current coil being negligible, this can also be either 75 volt or 100 volt reading. So, these are the list of equipments required for the short circuit test. Now, let us look at the open circuit test. The open circuit test is done on the LV side. With the HV side open circuited. Here again we need to measure the applied voltage, power, and the current. Now, open circuit tests are done at rated voltage. Since open circuit tests are done at rated voltage, it could have been directly connected to the source, but the voltage rating of the LV side may not exactly match with the voltage available. Therefore, here also normally a variac will be used. For example, the available single phase supply may be of 230 volt, whereas our transformer rated voltage is just 200 volt. So, we need a variac. So, now let us see what is needed. One is single phase variac. Its input voltage will be 230 volts. All variac will give you up a voltage at least up to input voltage. So, this voltage rating is sufficient. The current drawn from this variac will be the no load current of the transformer, which is very small. On the LV side, the rated current is itself is 20 ampere. The no load current of a transformer will be around 5% of that. So, the no load current will be within 1 ampere. So, even a output current, a variac that can give 1 ampere output current should be sufficient for this test. However, if we do both the single phase, the open circuit and the short circuit test, I can use the same variac that was used in case of short circuit test for doing this test. Now, there the output current was specified as 10 ampere, which is sufficient for to be used for the no load test. So, here also we use the same variac with the input of 230 volt and output current of 10 ampere. It should be emphasized that this 10 ampere output current is not required for this no load test. However, in order to reduce the duplication of equipment, we are using the same variac that we used for the short circuit test. Hence, this is sufficient. However, if the short circuit test is not required, only open circuit test is required, then we can choose a variac of much lower current rating. Second is the ammeter. Again, here also we will need a ammeter, moving iron ammeter. As we have already mentioned, the current drawn will be simply the no load current of the transformer. For this particular case, on the LV side, the rated current is 20 amperes, no load current I 0 is usually 5% within 5% of IFL. So, I 0 may be 1 ampere. So, again whichever ammeter we have chosen for short circuit test could have been sufficient. However, this current rating 10 ampere is too large for performing the open circuit test. The problem is, the higher the maximum range of the meter, the lower its accuracy becomes, particularly with moving iron equipment. At the lower end, the accuracy suffers. Therefore, it will be necessary to choose a lower rated ammeter. So, let us choose something like 3 ampere rated ammeter for this test, since the same 10 ampere ammeter will possibly give erroneous result. Sometimes meters with multiple ranges are available. For example, we can get an ammeter of 2.5 amperes, 5 amperes and 10 amperes, in which case the 2.5 ampere range can be used, same ammeter can be used for both the tests. With during open circuit test, we use the 2.5 ampere range, for the short circuit test we use the 10 ampere range. Similarly, for here also we will need a wattmeter. here also we will need a wattmeter. The wattmeter, in this case we will have a current coil rating which is same as the ammeter current coil rating. So, preferably 2.5 ampere, 3 ampere current coil rating would have been good. Obviously, this same wattmeter current coil will not be useful here, because here again we will have the same problem of accuracy. So, we cannot use a wattmeter with 10 ampere rated current, we will have to use a much lower 2.5 ampere would be ideal. However, it is difficult to get a wattmeter. So, let us choose a either a 2.5 ampere if available, or a 5 ampere rating for the current coil. For the potential coil though, here the applied voltage is same as the rated voltage of the LV side, which is 200 volt in this case. So, we will have to choose a wattmeter whose potential coil is rated at least at 200 volts, it should be more. So, we choose a wattmeter with a potential coil rating of, let us say, 300 volts. Most importantly, for getting accurate result, we will have to be careful about the type of the wattmeter. At no load, the power factor is very poor, it is close to 0, it is less than 0.2. So, this must be a low power factor wattmeter. The short circuit test also the power factor may be poor, but usually is not so poor as in the case of low power, in the case of open circuit test. So, possibly a normal wattmeter will be sufficient for short circuit test, but for no load test a special low power factor wattmeter which measures accurately below a power factor of 0.2 must be used. Finally, we will need a AC voltmeter, which is a moving iron voltmeter, and since they are connected the same points as the potential coil of the wattmeter, this should also be rated at 300 volts. So, to summarize, to do this test, the following equipments will be required. One is a single phase variac, (230 volt), 10 ampere, MIA 0, 2.5, 5, 10 ampere. If it is available, then 1, otherwise you will have to get 0 to 10 ampere 1 and 0 to 2.5 ampere 1. Voltmeter, you can get again choose a 0, 100, 0, 75, 150, 300 volts. This is a normally available voltmeter. You will need two types of wattmeter. One is LPF, current coil rating 0 to 2.5 amperes, potential coil rating 300 volts. Another normal wattmeter, current coil rating 0 to 10 amperes, potential coil rating 75 volts. These are the list of equipments which will be necessary for performing the short circuit and the open circuit test on this particular transformer.